Okay, so lastly, we're going to talk about how to do this with the t-test. This is what you use whenever you don't know the population standard deviations and whenever you have small sample sizes. So it's the same sort of criterion that we used in the previous sections to decide whether we could use the usual z-test or this non-standard t-test. This section is exactly the same, so we're still going to be using the same alternative and null hypotheses. The only thing that's different in this t section is that we need to change the distribution that we're using, obviously. So we're going to have degrees of freedom now because we're using the t distribution. And we'll also be computing the standard deviation and the test value in a slightly different way. But the formulas are basically identical. I think the main difference is that whenever you're looking up a t-value, like a critical t-value, remember that in this t-distribution table, you need to decide a number of degrees of freedom before you're able to look up the critical t-value. So we will know the degree of confidence that we want. In our example, we wanted a 95% degree of confidence, or in other words, a 5% area as our level of significance. But we don't know yet what our degrees of freedom are. For that, we need to use this formula here, that the degrees of freedom that you'll get in these cases will be, the minimal number of degrees of freedom between the two sample sizes. So for example, if I took one sample size of 10 people and one sample size of 20 people, then I would use the number of degrees of freedom that's smaller between the two. And in both cases, I'm computing the number of degrees of freedom in the usual way, which is the sample size minus 1. So the 2 degrees of freedom that I would get from those two samples would be 9 and 19, and the smaller of those is going to be the degrees of freedom that I use in the table. So in that example, I would be looking up 9 as my number of degrees of freedom. But aside from that, this is basically the same procedure as before. I would recommend, if you want just to be able to reference the previous example, that you pull up the notes in front of you while we go through example 3. I think it would be more jarring for me to keep scrolling back up and down than it's worth. So I think I'm just going to stay down here at example 3, and I'll just tell you what all of the values are from the previous exercise. But if you want to have that exercise in front of you for reference, then go ahead and pull it up. So in example 3, it says, change the sample size to 25 for both groups and use the following test, and then use the following to test the original claim at this alpha level. So the only thing that's changing here is that our sample size is now 25, which is under that critical value of 30. So this time we need to use the t-distribution. Now for our critical values, we can compute the critical values in the same way. Now because this is a t-test, and because it's a two-tailed test still, we'll have plus or minus this critical t-value. And now I need to look up the critical t-value using the table. Now our sample size in this example is 25 for both groups. So it agrees between both groups, and therefore both groups have 24 as their number of degrees of freedom. So the number of degrees of freedom that I would look up in the table will be 24. And I know that alpha is equal to 0.5, and we're using a two-tailed test. So we're using a two-tailed test with 0.5, and therefore I would use this column. And the intersection there would be 2.064. So that will be the positive critical t-value. So I can go back to the previous page, and I'll get my critical t-value of 2.064. But because this is two-tailed, I have to do the same thing that I did with the critical z-values. I'll have plus or minus 2.064. So those are going to be my critical t-values. And if you want, we can draw a little picture here. So what this is saying is that I've got some distribution here, and my cutoff values are going to be plus or minus 2.064. So that's determined entirely by my confidence interval or by my level of significance. So this has nothing to do yet with the data that we collected. This is just what we would require as our cutoff values in order to accept or reject the null hypothesis. So here all I've used is the table and my level of significance so far. Well, I guess I've also needed to know the number of degrees of freedom in order to compute these critical values. So I did need to know the sample sizes, but I didn't need to know the results of the surveys, for example. So these are our critical values, and now we want to know whether our test statistic ends up being more or less extreme than these values. So for this, we'll compute the test statistic. The formula is exactly the same as before. Except that this time our test statistic, I'm just going to call it t rather than z because we're using a t distribution. But it's still going to look like this. It's x1 bar minus x2 bar minus the difference between the means, which again is 0, so you don't really need to include that second term. And then we're going to divide by the square root of the sample standard deviation squared divided by its sample size, plus the second standard deviation sample squared divided by its sample size. So it's the same formula as before, I'm just replacing z with t and sigma with s. And now if we plug those in, what we'll get is a 15,675 minus 12,515 as the first thing in parentheses. Remember that second parenthetical term is 0 by the null hypothesis. And then we're going to divide by, here they didn't change the standard deviations on us, so I'm just going to assume that those are the sample standard deviations this time. But they did change our sample size. It's now 25. So this is the expression that we get as our test statistic. And if we plug all of that into a calculator, what we end up getting is 4.39. And now if we come back over here to our t-axis, what we find is that 4.39 is way over here. So it is more extreme than our cutoff values or our critical values. So we would reject the null hypothesis. You can do the same sort of thing with the confidence interval approach. Here the confidence interval approach is exactly the same formula-wise, with just this adjustment that this time we're using a t value rather than a z value, and the formula for our standard deviation looks slightly different. But it's basically exactly the same thing. I keep putting these too far to the right here. Okay, there we go. And then the only difference between these two sides is just whether you're adding or subtracting this quantity. So on the left side, you'll be subtracting t times the standard deviation, and on the right side, you're adding it, which is the same thing that you do in the z case. So this is the confidence interval that we'll get. And if we plug in everything, then maybe I'll go ahead and do this just so that it's easier for you to plug into your calculator if you want to test it on your own. I was considering just writing what I got as the final answer, but I think it might be helpful for me to just write the full thing. So here we'll have the difference between the sample means minus our critical value, which was 2.064, times the square root of the same expression. So this is 2880 squared divided by 25 plus a 2160 squared divided by 25. And that's supposed to be less than mu1 minus mu2, which is supposed to be less than that difference between the sample means again. This time plus 2.064 times the square rooted expression. I'm out of space. Oh no. I'll try to squeeze it. There we go. Perfect. Perfect. Perfectly legible. Okay. So in any case, you can copy the same square rooted expression from over here. So if you evaluate the left underlined expression, then what I got was 1673.92. That's supposed to be less than mu1 minus mu2, which is less than, and then this expression over here on the right, when I plugged that into a calculator, what I got was 4646.08. And remember that when you use the confidence interval approach, what we want to know is it possible for this middle number to be 0? In other words, could the null hypothesis be true? And in this case, we are confident that the null hypothesis is not true because both of these numbers are positive. 0 is not between those two numbers. So here we would again reject the null hypothesis, because here's our confidence interval. All right, and that's the end. That's all we got. So this is the last section of notes. We won't have any homeworks over this that I will collect, but I will be posting some problems that you can do optionally to prepare for the final. And this is it. So